Okay, so this is our last chapter. This is very exciting. Today we're talking about chi-squared tests for goodness of fit. If you took AP Biology, you might have at least have heard of these kinds of tests. So talking about M&Ms, when they produce M&Ms, they have a certain ratio. I think it's actually changed from here. Just from the M&Ms activities we've done this year, there's a lot more yellow and a lot less red than this seems to indicate. But this was maybe a couple years ago. This is how they used to make them. Maybe they changed because of cost, I'm guessing. Um, so Jerome's class wondered if the distribution of color in a large bag of M&Ms differed from the claimed distribution. Well, it's very possible. So here are the data from a random sample of 60 candies from that bag. So there were 60 in one bag. There were 60 M&Ms, and this is the breakdown. Okay. So the distribution, what's the null? And this is almost always the null. Now it's in context, but it's the same. There's nothing unusual. They say the stated distribution was that. We think they're right? So the null is the distribution of the color M&M candies is the same as the claimed distribution. So we don't have to list out each individual color. We can just say it's the same. The distribution is the same. What do you think the alternate would be? The alternate is we think it's not the same, right? We think there's a difference between the two. So we don't usually have to clarify, what we think at least one color would be different. You usually just kind of say, we don't think it's the same. So this is not testing. I think the difference between what we did before with the two prop was testing like we just did blue M&Ms or we just did yellow M&Ms. This is saying all of them. Is the distribution of all the colors the same, or is the distribution of all the colors at least somewhat different? So that's really the null and the alternate in a nutshell for this. We can write them in symbols. If you want to, probably not necessary. I much prefer, this kind of generic, in context, kind of talking about that. They're saying if you do use symbols, if you use the proportions there, you're not really suggesting that all the colors are different. When you say they're different, you're just saying the distribution is not the same. So at least one color is different or something like that. Okay, so how many candies of each color did they expect to find? So that's not too hard to figure out, if that makes sense. So to do that kind of a thing, you would just kind of take the stated percentages and multiply by 60 because that's the sample size, or n here. So 60 times 0.125. So those three colors are supposed to be, you would expect around 7.5 M&Ms to be brown, red, or yellow each. And those had some differing, so two of those were more popular. According to the breakdown, orange and blue are the most popular, and so those you would expect about 15 M&Ms, or about a fourth of the M&Ms to be orange or blue. So those are what you would expect. Now, when you take a sample, you're probably not going to get exactly what you expect, right? So you're going to find the differences there. So the expected count is n times p, where p is the proportion for each category multiplied by the n, the total number. Okay, so we have now we're sitting side by side. We have the observed and the expected. So it looks like we got more brown than we expected, more blue than we expected, but a lot of the other colors maybe not as many as we expected. So just kind of a different look of that. So, but a couple, that's very typical when you take a sample where there might be a couple that are just way off, kind of thing. How likely is the difference? Is this larger or larger occurred just by chance? Okay, well, that's kind of interesting. That's called the chi-squared statistic. So we're going to figure out chi-squared is going to be a number. By the way, that it looks kind of like an x squared. It's kind of like a cursive x or something there, but that's a chi. It's a Greek letter. So chi-squared is the name of the test. And so it kind of looks like an x squared, but you write it kind of in a cursive way. It's chi. This is, I believe, on your formula sheet. So if you look at the formula sheet, there it is. You don't have to memorize that formula. The chi-squared statistic is on there, so you can use that anytime you want. It's the sum. That's Greek symbol. The large uppercase sigma means the sum of the observed count minus the expected count squared divided by the expected count for each term. So you have to do that a bunch of times, right? So remember, if you look at that data we had there, so for Brown, it was 12 observed and 7.5 expected. So you would say the first one would be 12 minus 7.5 divided by 7.5, but the 12 minus 7.5 is squared. That's the first part of your chi-squared term. And then you do it for the next one. So if you look at red was 3 and 7.5. So 3 is the observed, so 3 minus the expected of 7.5 squared over 7.5. If you look back at red or yellow was 7 and 7.5, so 7 minus 7.5 squared. So each one of those 6 parts of that chi-squared are the different colors. They're of the M&Ms. We have 6 terms, one for each color. And you just add that up and do that, and it gives you the chi-squared amount. And so chi-squared is 9.8. So just a number. It's going to be a number here is what you're going to find. So let's just talk more about this. So Carrie made a 6-sided. So state the hypothesis that Carrie should test. Okay, so this is a slightly different situation here. So she made a 6-sided die in her ceramics class and rolled it 90 times to see if each side was equally likely to show up. The table summarizes the outcomes of her 90 rolls. So what's the hypothesis? We think that the stated distribution, in this case, what would the stated distribution be? That all of the outcomes are equally likely. It's equally likely to get a 1 or a 6 on this particular die that she made in ceramics class. So we think, the sides of Carrie dies are equally likely to show up, right? So that's the null. The alternate is we think they're not equally likely to show up. So it's always kind of like that not equal to. It's that they're the same as the null. They're not the same. The distribution is not the same, or what we expected, I guess. Okay, so calculate the expected count. So again, you're going to plug into that formula, the observed minus expected squared. So this one for the first one would be, if you think about 90, so 1/6 of 90. So what is that? So if you do 90 times 1/6, you get 15. So we would really expect 15 ones, 15 twos, 15 threes, 15 fours, 15 fives, and 15 sixes. We expect 15 every time. We didn't get 15 every time. We got 15 sixes. We got a ton of twos, right? So we got some of those we got less than we expected. So you're going to just fill out the chi-squared statistic for each one of those, right? So the observed were all different. The expected is actually always 15 right there. So you just take the 12 minus 15 squared over 15, 28 minus 15 squared over 15, and calculate that, and you get the 14.41. So wow, that's a lot of work. They use software to simulate 1,000 random samples of size 60 of this situation. This is what they came up with. So this is a simulated R squared. So again, our R squared value was 14.41. So, or was it, I'm sorry, I think we're looking back to the chi-squared for the M&Ms. What did we get for that one? 9.8, I believe. Sorry, looking back at that one. Okay. So 9.8 falls where in the spectrum here? So we've got you count them out. You go, okay, there's 87 of the 1,000. That'd be hard to count, but you do it. Of the 1,000 samples, were that extreme of 9.8 or even more extreme than that, right? So that's 87 out of 1,000, which is 0.087%. That's pretty small, right? So that's less than 1%, 0.08. 0.087, so 8.7%. I mean, I guess it's not that small. Chi-square distribution is defined by the density curve that takes only non-negative values and is always skewed right. So that's interesting. We've been dealing a lot with normal stuff. So chi-squared is always going to be skewed right. It maybe makes sense as to why that is, because the degrees of freedom is going to make it look more normal potentially if it increases. So if degrees of freedom is small, it's just going to be straight skewed right, like almost like a falling graph there. As it gets a little bit bigger, it starts to look like a normal kind of skewed right. You just kind of take normal graph and skew it right. As the degrees of freedom gets bigger, it actually starts to look a little bit more normal, just in general. I really like you write these down in your notes. As degrees of freedom increases, it becomes less skewed. So at least less skewed, maybe more normal. The mean of a particular chi-square distribution is equal to its degrees of freedom. Well, that's kind of a fascinating stat you would not expect. But the mean of chi-squared is always equal to its degrees of freedom. So if the degrees of freedom is 8, you would expect the mean to be 8. If degrees of freedom is greater than 2, the peak of the density curve is at degrees of freedom minus 2. So that's not how to calculate degrees of freedom. That's the peak of the graph. So if you look at this one, degrees of freedom 8. So 8 minus 2 is 6. 6 is right about the max on that graph. For the red graph, 4 is degrees of freedom. So 4 minus 2 is 2. It looks like the peak is right about 2. It doesn't work for degrees of freedom 1. It's got to be bigger than 2 for that little trick to work. There are 6 colors. So the degrees of freedom is n minus 1, so it would be 5. Which means the peak would be about 3, right? And it's going to be skewed right. The p-value is the probability, and the mean would be 5, of getting an x chi-squared value as large or larger than 9.8 when the null is true. So what is that chance of it happening? Well, so this is a chi-squared curve. And so, of course, the calculator is going to be able to do this. I mean, you kind of know that. So you could do that in the table, but you could also do it using this command. So you could go to menu, I'm sure it's under statistics, probably distributions, and it might say instead of norm CDF or TCDF, which we've used in the past, it's going to be chi-squared CDF. And so you have to put a lower bound, in this case, probably negative infinity. Upper bound was 9.8, we think. And degrees of freedom was 5, right? Because 6 minus 1 is 5. And it should give you the chance of that happening. Whoops. Oh, okay, let's do that again. Sorry, it's always skewed right, so you always go to the right. I don't know why my brain was going left here, but it's going to be that extreme or more extreme, so you're always going to the right. So the lower bound is going to be 9.8. The upper bound is positive infinity, and then degrees of freedom is 5. And that's why you get, anytime you get a p-value here of 90 over 90%, you're thinking, man, I wonder if I went the wrong direction there. And that's what I thought when I did that, because I went the wrong direction. So this p-value is between 5% and 10%. Failure to rejection, that doesn't mean, we're not saying the null is true, we're saying we can't prove it wrong, right? That's the idea of that. So again, you could just use technology to figure that out. So for this one, member, our chi-squared value was, if I can read that, 14.41. So if you go to chi-squared command menu 6.5 chi-squared CDF, so 14.41 to infinity, and degrees of freedom was 5. Because there were 6 rolls in the die in this one. And so it would be 0.0132. So you can figure that out just knowing that information. Okay. The Hershey Company makes the Reese's Pieces claim that distribution of colors is as follows. 50% orange, 25% brown, and 25% yellow. If you've had Reese's Pieces, you know there's a lot of orange ones. Skeptical of this claim, Trey purchased a very large bag of Reese's Pieces and selected a random sample of 80 pieces. Here are the results. What is the hypothesis that Trey should test? Well, nothing unusual is going on. The stated distribution is correct. What's the alternate? The stated distribution is not correct, right, for Hershey's Reese's Pieces. Calculate the expected count for each one of these. So how many would we expect if he purchases 80 pieces, so 80 times 0.5, we would expect 40 oranges, and 80 times 0.25, we expect 20 browns and yellows there. 20 of each of those. So those are the expected amounts. Well, you didn't get those exactly, right? You got 31, 22, and 27. So, a little bit different. How different is it? Well, let's apply the chi-squared statistic here. So you're going to, plug in the numbers here to get this. So you'd say 31 minus 40 squared over 40 plus 22 minus 20. You're taking the observed minus the expected over expected. And add up those three numbers, and you get 4.675. By the way, I didn't mention this before, but it's kind of interesting. So which one was the biggest contributor? Sometimes I ask a question like this about contributors. So what I mean by that, which one was the most unusual compared to what we expected? Well, you look at these three numbers at the bottom, 2.025, that's for orange, 0.2 is brown, and 2.45 for yellow. So brown had very little effect on chi-squared. It was pretty close to what we expected. We expected 20, and we got 22. Yellow was quite a big contributor here, 2.45 of the 4.675 chi-squared statistic. So yellow was the most different because of the three numbers, that's the biggest difference there. So you can kind of even tell which one was the most unusual when you do this. So we figure out that chi-squared was 4.675. Find the p-value using your TI-Nspire. Okay, so let's try that. So menu 65 and go down to chi-squared, CDF. We're using our 4.675. Upper bound infinity. We're always going to the right with chi-squared. Degrees of freedom is it 2? Let's see. Yeah, degrees of freedom is 2 because there were 3 colors, right? So 0.0966. There you go. So that's the method of doing that. Okay. Let me show you one more thing, maybe. Okay, we might go over this again for the next lesson, but I'm going to go ahead and show you now how to do this test in your calculator because you probably guessed you can probably do this in the calculator, and you can. So you have to have the observed list and the expected list. So I'm going to do that. So I'm going to hit the home key, go to list and spreadsheets. I'm going to call it exactly that, observed or OBS and expected. Oops. It looks like we can't use EXP. It must be a command in Excel or in TI-Nspire. So observed, we're going to put in 12, 28, 12, 13, 10, 15. Okay, and the expected 15, 15, 15, 15, 15, 15. Okay, so now we're going to go to the calculator page. You got to be connected. Don't go to Scratchpad. So menu 6. We're doing a test, number 7. And there it is, chi-squared goodness of fit. There's 2 different chi-squared. You definitely want the goodness of fit for this one. That's going to test the whole distribution. You have to have an observed list. We have that. You have to have an expected list. We have that. And you have to say the degrees of freedom. In this case, that is 5. And it will do the test for us. The chi-squared, remember that number 14.41? There it is, the p-value 0.013, degrees of freedom. It even gives you the comp list. What in the world is the comp list? If you hit the variable key and go to comp list, it tells you which color, which number contributed to each one of those. So that number 1, rolling a 1, it was 0.6, part of the 14.41. Wow, rolling a 2, look at that. It contributed 11.2667. That's the bulk of this. I mean, 2 was so unusual compared to what we expected. That was the biggest contributor to the chi-squared statistic there. So it actually breaks it down and does each one for you. So oftentimes what we do here is we'll show a little bit of the work. Like we'll start showing the chi-squared work, but we won't show all 6 of those when we show our work. Maybe show the first and the last with the dot, dot, dot in between, plus, 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 kind of thing. And I'll show you that in class when we do that. Okay, that's your lesson for today.